Good morning. Welcome to the second session of the second day of the SANSAM workshop. I am delighted to be chairing this session with my colleague, Dr. Tokik, also from MIT. I'm Dick Yu from MIT. And this morning we have an interesting session with 5 presentations, generally around the theme of integrated solutions for offshore monitoring, modeling, and utilization. I looked through the titles of the talks, and I think it's going to be a very exciting session for all of us. And I look forward also to very stimulating conversations and discussions that the presenters would invite us into. So the first talk is by Eric Adams of MIT, and he's going to talk about the dynamics of sediment clouds, clumps, and plumes with application to land reclamation and dredging activities. So let us welcome Eric. Yeah.
Thanks, Dick. Since this is perhaps our last opportunity to make a presentation at a SANSAM workshop, I want to make sure to thank our sponsors for this and the opportunity we've had to work on this project for the last 8.5, 9 years. And also like to acknowledge all the researchers on our team, past and present, and to say proudly that those who are in the past mode have all gotten good jobs, and those that are in the present mode seem to all have good job opportunities, which I'm happy for. So, as you all know, the reason that we're interested in this topic is that there is a lot of sediment being moved around the world in coastal waters. The price of sand has escalated significantly. It's a valuable resource, and if it's also not placed properly, it can become a contaminant. The turbidity and, in some cases, the associated chemicals that are associated with the sediment are contaminants. And so we're interested in the understanding of how sediment moves when it's intentionally placed in coastal waters. So I just sort of summarize what it is that we have done. I think we've done in the last 9 years or so. We've spent a lot of time looking at the fluid mechanics of the various flow structures that result when sediment is put into the water in continuous or instantaneous form above the water surface, below the water surface, etc. We, probably the best word is to say, rediscovered a flow structure that is quite important. That's what we'll refer to as the clump. We have taken this understanding, which mainly has to do with near-field fluid mechanics, and we've integrated that into a far-field three-dimensional circulation model to extend the length of our simulations from scales of the water depth to kilometers or so away. And we have put various models into an umbrella package, which we call BSDM, Barge Sediment Disposal Model, which we're now in our second version, and it's receiving some attention from users in the field. So let's start off with where we were, or where the state of the art was. It dates back to the late 1970s when Cohen Chang from Caltech and Tetra Tech developed a model to try to explain the behavior of sediment thermals or clouds when they were released instantaneously into the environment. And they had a simple, effective, but in many ways very simple model, saying that this is a uniform structure that descends because of its negative buoyancy. They acknowledge that sometimes sediment that's released doesn't all get into this thermal, but they only had ad hoc ways to quantify that. And if you waited long enough, the sediment particles would eventually rain out of the thermal, which descends, it decelerates, and they had a fairly primitive way of acknowledging that. So we have tried to improve our understanding of these various parts of the plume and how they are affected by various conditions, including the ambient conditions, waves, currents, stratification, and turbulence. So Adrian Lai developed a model of the internal circulation. He borrowed from the Hill's expanding spherical vortex model to describe what the flow circulation is that's inside and outside of these thermals. And the advantage of that is that he can use that to drive the circulation of the particles inside with a Lagrangian particle tracking model, and that allows the particles to rain out of the plume in a swarm that is continuous as opposed to instantaneous. It also allows for different size particles and the whatnot, so it gives a much better description of what's happening. And if this works, you can see a simulation of the measurements versus the simulation that does a pretty good job of reproducing the character of this phenomenon. And as I said, it also works for various sediment sizes, so you can have sequential settling of particles out of this plume. So one of the big issues is how much sediment does not make it into the plume. It's hung up in the so-called trailing stem. There was some research done by a previous student, Gordon Rugaber, who was from our group but was not part of this project, and then Jim Gensheimer, who was part of this project. And so Adrian, again, has tried to summarize this information. This is the fraction of the released sediment that is found in the trailing stem, and that is vulnerable to being dispersed in the environment when there's waves, currents, turbulence. And that increases. This is 5% all the way up to 100%. These are different release conditions. This is a normalized ambient current, and going in this direction is the normalized settling velocities of the particles. So as you get the smaller particles or faster ambient currents, you tend to get more mass in the sediment, in the trailing stem, and hence more vulnerability to pollution associated with the dredging or land reclamation events. And they're somewhat different, but the same trends for different types of release conditions. We also had a theoretical basis for this. We did a lot of numerical modeling, and this is the only aspect of that I will talk about. But Rochen Wang looked at the development of starting plumes and vortices through large eddy simulation, and he built upon earlier work by Garab et al., who identified the behavior of the sediment thermal, or in his case, a vortex, and how it relates to the amount of fluid that is introduced into the environment. In this case, he was using a piston to try to generate a vortex. And it turns out if the stroke length divided by the diameter is larger than a certain value, that certain value is around 4 for neutral buoyancy, all the material does not make it into this recirculating vortex structure. If it's less than that, it does. And one of the things Rochen did was to look at what happens when you add buoyancy. So this is, instead of just a jet, it's a buoyant jet, and the buoyancy is increasing to the right, and this critical value of L over D goes from about 4 up to maybe double that. And that at least gives some insight as to the duration of a discharge, over which time all of the material will be assembled within the parent thermal. So as I said, we looked at the behavior of these thermals under a variety of environmental conditions. And I guess the simple motivation was to see if we turn up these environmental conditions, can we reach a point where this thermal stops becoming a thermal? Can we break it up? And so we first of all tried to do this with waves. And it was a nice study, but as far as we could determine within the limits of our laboratory experiments, which scaled up to field waves of about 2 meters and 9 seconds, we couldn't get the waves to destroy these thermals. They would descend, they would follow the orbital velocities with just a slight lag due to their inertia, but they would basically end in the same spot that you would be able to predict. So waves did not appear to be a problem, at least within the typical environmental conditions you would find in coastal regions. Not the same story with currents. Jim Gensheimer looked at the behavior of thermals in sediment thermals in currents. This again is a normalized ambient current speed. This is a normalized but differently normalized particle size. So this gets to be small particles, this gets to be high ambient currents, and that combination moves one from what he defined as weak currents to strong currents being strong enough to blow apart the structure of the thermal. And so basically this was parameterized into an equation, and if you apply that to the field, you can identify the conditions where it would be safe to release sediments and those where it would not be. And in this particular example, if you took a cubic meter, which is typical of a dredge bucket, of fine-grained sand, this transition halfway in between this strong and the weak was about 0.6 meters per second. So if you have tidally reversing currents, there would be a window of time when it would be acceptable to release and a window of time around the max flood, max ebb, that it might not be. So as part of this project, we built a large tank. You've probably seen it on the first floor of the laboratory building. We call it the Houdini tank, or sometimes the Houdini tank number 2, since we have one at MIT. And one of its claims to fame is it's got a pulsating jet array that produces turbulence, shown schematically here. These are simple bilge pumps that are programmed to come on and off at random intervals and produce homogeneous turbulence. And we've done a lot of studies as to just how clean that turbulence is. And Adrian Lai has done a lot of work characterizing the effects of turbulence on plumes. One of the key simple features is just to ask how much turbulence, in analogy with how large of the waves or how strong a current, how much turbulence is necessary to have this plume break apart. And it turns out ultimately would break apart, but what is the depth? And it turns out that depends on a buoyancy flux, how much flow of how dense material is coming out. Beta is simply a spreading length. It's typically about 0.1, and epsilon is the rate of kinetic energy, turbulent kinetic energy dissipation. So it's an indication of the turbulence. The stronger the turbulence, the shorter this depth, the greater the buoyancy flux, the larger that depth. And we try to find out how this compares with what real conditions are. So for coastal sediment discharges, there really should be a range here, but these values, 1,000 meters, are way larger than typical water depths. So turbulence does not seem to be a problem as far as coastal sediment discharges is concerned. We looked at wastewater discharges, and they might be on the margin, but probably not. What we think is actually an interesting area to explore would be indoor air quality and ventilation and convective plumes due to human activity. And so the typical depth lambda is around the ceiling height. So it's probably important in a case like that. And lastly, we've been looking at stratification. Cindy Wang has done some experiments at MIT. She's continuing those experiments here at CREATE. The experiments at MIT are in a towed stratification tank. And so she stratifies it and tows it. She's looking at the depth at which the plume intrudes into the ambient at a level of neutral buoyancy. That's a declining function of the current speed. She's also looking at the deposition. This is increasing particle size, and so the deposition patterns are becoming shorter and shorter with denser, larger particles. And the experiments and a model that she has show good agreement. So I want to talk about this new formation that we've identified or kind of rediscovered, and maybe we can get it back. we can't. Maybe we can. So on the left, we have a sediment thermal that's made up of relatively coarse material. On the right, we have a sediment thermal which is in all ways equal, except that it's finer grain material. It's finer grain, but it's not cohesive, so it's still non-cohesive. But you see dramatically different behavior. One of them is holding together as a sediment thermal. The other one is sort of falling apart as a clump, forming a wake. And so we've had a lot of fun trying to extend these observations into some theory. On the left, we see another way to represent this, but again, this is the descending thermal. This is the clump. And these are distinguished by a value of this cloud number that's about 0.03, probably only good to one of those significant figures. And we've argued, and I think proved theoretically, that the behavior and the distinction of this behavior has to do whether or not flow can flow through this porous cylinder or porous sphere. If you have relatively coarse material, the porous cylinder or sphere can settle through the water, and the water will help create this thermal. If it is not the case, it'll go around it, and you'll get this clump formation. And this cloud number, again, is a settling velocity divided by a characteristic size of the thermal. So larger thermal radius or smaller settling velocity tends to promote this clump-like behavior. And the interesting aspect of this, perhaps somewhat problematic, is that if you take a given grain size and you go from the lab, where you might typically be in a cloud formation, you take that same sediment size and go to larger volumes, as in the field, you're attempted to get into the clump formation, which means it may be harder to find thermals in the real world. So we've taken this information, we've put it into far field models. In general, we could use any number of available three-dimensional models. We've been using EPA's model, EFDC, and basically we've represented the loss through the trailing stem and also the swarm formation and how that gets in the environment. We've included algorithms for sorption, desorption, even stratification and whatnot. And we have we have a little video, but I'm not able to get that at this point. We'll look at the last thing, which has to do with gravity currents. And these are important. Once the sediment reaches the bottom, it starts to spread. And we've developed a better model, a box model, to look at these gravity currents that are neither circular nor two-dimensional, which are the two endpoints that people have used. But Genway Air has developed such a model, and experiments and observations of deposition patterns agree quite well. So we've taken all these models and we have put them into a umbrella model, which, as I said, was called the Barged Sediment Disposal Model, BSDM. So we have a classification scheme that, depending on characteristic length scales in the environment or of the discharge, one can categorize the plume behavior as one of about 8 different categories. This is patterned after sort of a similar structure that is used for sewage plumes, desalination plumes, and whatnot, called Cormix, and this is our version of that here. And so we have little modules for each of these, and they're packaged together. We've put them into a model. We are offering this free of charge. You can take a look at a little more information about this in the website here. And we've had interest from a number of organizations, principally the companies that are involved with dredging operations, dredging and land reclamations in Singapore that are required to comply with regulations. And that's it. Thank you very much. So I probably saved you 2 minutes, right?
Okay, while we have the next speaker preparing for the talk, we'll open the floor for any questions.
Mañana.
Later, we have the Q&A.
Yeah, later.
Okay, maybe we can save it then for the panel
If not,
section.
let's thank Eric Adams again. The next talk is titled Distributed System of Autonomous Buoys for Scalable Deployment and Monitoring of Marine Environment. And it will be presented by Roland Bouffenet of SUTD.
Thank you very much, Dick. Good morning, and I'd like to thank the organizers for giving me the chance to present this work. It's a joint work with DQ at MIT and the team that I will present later on. Before I say more about this project, I'd like to give you some background about this. Dick and I, we are latecomers to the CENSAM effort. Essentially, we submitted a pilot proposal 2 years ago. And so back then, we had a vision, and really, it was just purely a vision. And I'd like to share with you briefly what was submitted. So our proposal was indeed, about monitoring the environment with large numbers of, dynamic sensors. And so we proposed to design and develop a system with, robust monitoring, for large extents of the marine environment. And the idea was essentially to have swarming, dynamic cooperative swarm of mobile sensors. We looked at a large number of them, like 100 or more. And we considered small buoys, and I'm saying that because most of the buoys you have in the environment tend to be, that are deployed, are typically bulky, expensive. So we were considering inexpensive, or rather inexpensive buoys, and many of them. And of course, we had to work on how to dynamically deploy them, because many of the features we have in the environment, as Eric Adams showed, are like thermal plumes. They evolve over time. They are under currents and changing environments. So we were that was the vision. Then last year, essentially 1 year ago, we had the CENSAM Scientific Advisory Board in Singapore, and we got a chance 1 year into the project to just present some of the ongoing results. So what we had at that time, 1 year ago, was a first prototype, which is shown on that slide that was presented to the SAB. And we had some field results in Boston and in Singapore as well. That was it. So since then, this is just, I want to acknowledge the work of the team. We had a joint team from MIT and SUTD working on this, and there are other people, and most of them are in the room, but we have other people from my team that have been helping on that project. So essentially, over the past 2 years, this is what we have accomplished. So I will present in greater details the goals and objectives, just going to piggyback on the vision we had 2 years ago, but essentially the same goals and expand on it. I will then, look at the robot itself, the autonomous buoy design, and then talk about the system, the swarm of buoys. The core of it, we have swarming, so this is control strategies. So I would say a few words about distributed communication, but I'd like to spend more time on showing you some of the interesting results we have obtained in terms of validations and specifically in terms of field test. All right, so goals and objectives, they were very much, and they are still very much aligned with the mission of CENSAM, so that is pervasive monitoring of coastal and inland water environments. This was explained yesterday by Professor Whittle. And in our case, we are interested both in nearshore environments, and we are also interested in the reservoirs. Singapore has many of these reservoirs, and they are interesting processes. PUB has several issues to deal with, and we felt like this system could be interesting for both coastal environments and reservoirs. So if you look at the existing solutions and techniques, essentially you have single autonomous surface vehicles. They tend to be expensive, large, we say very expensive. And of course, because they are just one of them, they are limited in terms of the surface they can monitor. Now, if you try to look at larger extents of water, well, you can deploy an array of sensors, but this tends to be fixed. And the challenge is, do you have the right resolution? Are you capturing the features? Do you have your sensors at the right location? And having a lot of sensors is going to be very expensive, and then most of the time you will have many sensors that are going to be useless. So we felt, and we still feel, that there was a real pressing need for small, low-cost, and rapidly redeployable autonomous buoys. These two systems, the single ASV, it's not going to be a good job at going to the place of interest. And the fixed array of sensor, as we said, it's going to be very hard to scale it to a large environment to monitor. So that's why we were interested in tracking some dynamic features in the environment. What happens when you have something like a thermal plume, or if you have an oil spill, variations in pH and salinity, for instance, in some of the reservoirs in Singapore. That's like for Marina Bay Reservoir, it's a big challenge. Do you want to know if there is an influx of salt, where it's coming from, and other examples, again, that were presented yesterday by Professor Whittle. Problems of algae bloom. These are just motivations. I'm not saying that we have found a solution for that, but we have a system that is capable, with some extensions, to look into tracking these dynamic features in the environment. All right, so let me first give you a snapshot of the overall system design before I delve into the details. So we use the multi-robot system approach, and our system is called Bob, right? That's his nickname. There are many reasons why it's called Bob, but band of buoys, bunch of buoys, and many others that I won't mention today. But essentially for Bob, what do we have? We have a bunch of mobile autonomous buoys. They are versatile in terms of sensing. I'll say a few more words about the sensors that we have been able to equip that buoy with. There is distributed communication. That's a technical aspect, but it's quite fundamental. And of course, at the core of it, what we have is these control strategies, cooperative control, and by that I mean swarming. Okay, that's what it is in the biological world. So why swarming? Why is that so important to that problem? But number one is, as we said before, it's a problem of scalability. Okay, today I'm going to work on a Marina Reservoir, then I know how many buoys I need to have, but tomorrow I need to go into a larger lake. Will my system be able to scale to that environment? And if I want to go to the marine environment, then it's even larger. So this issue of scalability is very important, and many systems, they are like designed and limited to a given size of system. So for swarming systems, they are like theoretically scalable to any size. Robustness is very important as well. So I think all of you agree with me that when you deploy something in the marine environment, well, it's very hard to get it back, to fix it. Agencies like NASA, for instance, when they send something into space and it breaks down, it's a disaster. So of course, the idea here is that if you have many of these units and one or two or more breaking down, well, at least your system continues to operate. So robustness is something that it's a feature that we really wish to have. And flexibility, all right, so I'm using the specific word by, swarm roboticists. So flexibility means that the system is capable of adapting to changes in the environment, all right? You have changing circumstances, and then your system will by itself be able to adapt to it. And if I go back to my slide on goals and objectives, since we want to track a dynamic feature in the environment, well, we want the system to be able to sense the environment and react upon it, and then move in the right direction. So flexibility, or people call this swarm intelligence, but I think it's a bit of a buzzword. Flexibility is really something that is interesting to achieve this dynamic tracking that we're looking for. Right. So I'm going to delve into the details, and this is a very busy slide, but it's on purpose, right? It's a laundry list. So typically laundry lists tend to be busy, but this is just to show you all the things that we have taken into consideration. So at this point, I'd like to say that the original buoy is coming from Professor Yu's group at MIT. It was meant to do something else, and I'm not going to say what, but essentially it was evolved and redesigned to fit the purpose of that project. So what exactly do we have on our laundry list? Well, we wanted it to be compact, all right? Big, bulky buoys are already in the ocean, and they are very hard to redeploy. Yeah, there are like technical considerations for us. When we go to the field, if you have to carry 50 enormous buoys, well, it's good for your exercise, but it's also like a bit of a problem. Storage is another practical issue as well. So we wanted to have something compact, right? Less than a meter. Right now we are in the 30 centimeter size. It has to be omnidirectional, right? It's an autonomous surface vehicle, but it has no head, no tail. It's capable of moving in any direction, and this is thanks to vectorized propulsion system. Self-righting, of course. Robust. Okay, this robust is different from the robustness in swarming. It's robust in the sense that we want to test this not in the comfort of the lab, but in a real environment, right? You go at sea. We had a chance to go to the fantastic facility at St. John's Island, and Cyril Natio will say a bit more about this later on. But when you go to sea, biofouling, all these problems come into play, so you really have to consider that. It has to be low cost, right? Especially in Singapore, where everything, cost is very important. So we're proud to say that we essentially managed to do 50 units for the price of one. I'm not going to tell you the price of one. But essentially, we're pretty proud to have achieved that. Also, keep in mind that when you make 50 units, you have all these problems of quality control, ensuring that there is no variability in all the prototypes because they're supposed to work together. But it was I think we have been doing our job in keeping the budget pretty low. The system is also expandable, right? For future developments, if you want to make a new prototype, if you want to add more sensors. So we we made the right choices in the beginning such that we've been able later on to add more features to the system. It's also computationally powerful. So you're probably wondering why I'm putting this. This sounds very much like a marketing, a brochure. But this is very important. We want to have a computer on board because there is a lot of computation to be performed, not just by the controller when you do swarming, but when you do the data processing and how you can use this data simulation to essentially compute a model and then get the system to move in the right direction. So we have a single board computer, which is almost as powerful as this MacBook Air. It's also versatile in sensing. We've been able to do temperature, pH, salinity, dissolved oxygen, and the software part is not just hardware. We had an initial software pack that was different, but we moved to the open system, ROS, Robotic Operating System, that we expanded, and I think that was a wise choice, yeah. All right, these are just a couple of snapshots, right? My previous slide was very busy with the laundry list, but now you can see the CAD model. We did the entire PCB design of the electronics. As an engineer, I cannot help but show this, schematic diagram. If you want to have more information, we have this paper that is going to appear in Autonomous Robots, and there are 11 pages dedicated to all of this. So we've been very thorough in the analysis of that and the design. Right, let me move on to swarming. What is swarming? If you turn to nature, what we know, we see that, amoeba are doing that, bacteria are doing that, birds are flocking, schools are, fish are schooling. Essentially, these behaviors, these collective behaviors are emergent. They are the outcome of repeated local interactions between the different units. And that's exactly what we want to mimic, in a sense, with our system. So the goal for us is, of course, we're not interested in just copying what the birds are doing, right? There is no point, having a school of buoys. There is no predator, right, for our buoys. So we need to design a collective action that is relevant to the problem we're trying to solve. And the challenge, of course, is how do you map a global level collective action with local rules? Because what we do, what we change is what we define are the local rule at the buoy level. And this, turns out, to become an emergent behavior. So that part is rather complicated. So I'm going to show 2 slides now with simulations, right? And later on, you will see the actual behavior in the field. But essentially, the way we have been doing that is by having building blocks behaviors at the local level. And by putting together these building blocks, you are able to get a collective behavior at the system level. So if you look at School of Fish, for instance, typically what you have 3 basic behaviors: avoidance, alignment, attraction, the AAA, as people say in the field, nothing to do with the Automobile Association of the US, but yeah. What is it? Well, when fish are schooling, what they want is they want to travel together. So they tend to look at one another and average the direction of travel. So that's alignment. And at the same time, they feel comfortable if they are close to one another, all right? That's the goal when you have a predator attacking. Essentially, by being very close to one another, you're confusing the predator. So there is attraction, and attraction is it's coming from vision. They see one another and they get very close. And then you have pressure sensing. Fish have lateral line pressure sensors. And this pressure sensing allows them to maintain a very short distance between one another. So they don't bump into one another. So these are the kind of things, these are some building blocks that you have for fish that we want to mimic with the system. So when we do these cooperative control, we can perform simulations. So that's exactly what we have on that graph. So in these simulations, we have 49 buoys, all right? And these are, I want to say these are simulations, all right? These are point particles. They have perfect mobility, but still, we want to see how they react. So we start with, we have one intruder here, and this one wants to essentially go through the pack of these buoys, and we want the others to essentially move in order to give way to these buoys. So as you can see here in light gray, you have the trace, if you want, of these buoys. Those that are quite far away, they are essentially not moving. So it doesn't seem like a big deal, but all of this is decided by the agents themselves, all right? So we don't tell them where to go. They decide where to go based on how the others are doing. So you can also do bypassing. You can also try to sneak in when you keep the buoys fixed. So we use a lot of these simulations essentially to guide us in the design of the swarming strategy. All right, I'm going to show another simulation here, and this one is interesting because we have performed the actual experiment in the field. So what do we have? This is the classical area coverage problem, where essentially you're given a surface and you put some agents in it and you want them to maximize the coverage of the area. So what we have here, we look into scalability issue. You go from 10 to 20 to 50, and then you see how the buoys are properly packed into it. Because it's a simulation, they are very nicely packed. But what we have been doing is we have been challenging that. This is essentially what people have been doing all along, right? But instead, what we're doing is we are changing over time the surface, the environment, the surface area that you have to cover. So we go from a disk to this kind of peanut shape. We chose that surface area because it's really challenging the system. So the buoys have to decide among themselves how to redistribute into this new shape. And of course, we look at that when you increase and change the number of buoys. Okay, I'm going to skip, for the sake of time, I'm going to skip distributed communication, but this is a very technical term. Essentially what we have a mesh network that allows us to push the information in the system so there is no central controller. If we want to have robustness, the system has to be completely distributed. So the communication we have is entirely managed by the buoys themselves. Right. Let me go to the validation results. First test we did, okay, this is in the field now, right? It's not a simulation. What you see here, these are the dot represents the GPS tracking of each and every buoy. They start, their initial position in blue. The red dot represents halfway through the process of aggregation, and the black dot is the final position. So this seems like, we pushed on the button and all of them went into that direction. What I want to say is what we did is we put them in the water and then we told them, now you decide, you aggregate. All of this is based on a consensus algorithm, right? So we don't know where they are going to decide to go, right? So the buoys themselves decide collectively on the locus of aggregation, and that's what was achieved on a fairly large area. This was performed at Bedok Reservoir, by the way. All right, another test, which is also interesting, is it's a collective behavior called leader-follower. What you have is you have one buoy that you control, or you can say it's a selfish buoy doing its own behavior, and all the others are doing a consensus behavior. And you take control. So what we did is we took control of the buoy that has the tracking, the blue line here. And as you can see, all the others followed, except for that one. Right? So we're showing this one. This one had a battery problem. And we highlighted this because this is showing robustness, right? There is one that is lagging behind, misbehaving. Well, the system, as you can see, it's not bothered by one that is left behind, all right? So I can reassure you that we got it back. We went with the kayak, and the kayak is not shown here, and we got the buoy back. But the system continued to operate properly. Right, let's go to the actual problem of dynamic area coverage. So this was performed again in a reservoir. What you have here is the field view. I wish we could have a top view, but you're not allowed to fly drones, so we're in this area, so unfortunately. So we have a side view, it's exactly matched. So you're going to see here the GPS position real time with the video in the field. It was raining on that day. Before I turn on the video, what is going to happen? Well, you're going to see that the buoys here, I think we have 20 of them, they're supposed to, in the field, they're supposed to map or like cover this area, and this surface is going to change over time, and you will see how the system is going to respond. Right, there you go. So they're moving. I'm sorry, the video is not very good, so this is something that we need to improve here. But you see that the domain is changing into this peanut shape, and the buoys by themselves, right? You know, we're just watching and taking pictures. They are redistributing themselves, and the system goes back to the disk. And again, the buoys decide what to do real time. I think we lost one as well, but the system continued to operate. If you lose one or two, we did that test as well. Well, essentially, they will redistribute in the space. Okay, right, that's nice. Now, a couple of results, and I'll just finish there. These are the views in the field that we have just seen. So we performed a scalability study. What happens when you inject more buoys over time? So we started with one, and then the only thing they have is a goal. You have this surface that you need to cover, and then we added more and more and more, and here you can see that this is a metric that measures the effectiveness of the system, and you see that, you know, your effectiveness, essentially, the effectiveness is the inverse of that, so your effectiveness increases when this decreases. This is based on the tessellation of the space. All of these are based on field results, right? Showing very good scalability. This is now showing flexibility, right? This is something that very few people have been, we're very proud of this because very few people have been able to test the ability of a swarm robotic system to dynamically redeploy real time. So you go from the disk to the peanut shape, and in blue, we have what, you know, essentially the simulation will give us, which means that you have a perfect buoy, and our buoys are far from being perfect. So you have a perfect buoy, and you will obtain essentially this kind of metric, and our system performed quite well. Now, let me just conclude now. Essentially, this system, we received, you know, some compliments from the reviewers, which is so rare these days that, you know, I feel I should mention it. Right, and I can feel that I'm not the only one, you know, having these experiences. And so we were pleasantly surprised to read that people were acknowledging that this was really state of the art. However, they had a couple of comments, but that's a fair game. So people are realizing this is a state of the art system, and the main reason, like 2 reviewers said exactly the same thing. Very few of these tests are actually carried out in unstructured environments, in the absence of any supporting systems. As I said, people typically do that in labs, and you have overhead cameras and things that are helping. No, this is for our system. It was in the heat of Singapore, in the humidity, us sweating, especially my researchers. And, you know, the results are, you know, speak for themselves. Now, moving forward, we are going to start working on heterogeneous swarming. We have many ideas, but Pablo Valdivia is going to give a talk later on, and we just almost get a grant, right, to start working on his soft robots swarming with our buoys. So we're pretty excited about this. There is another thing I mentioned earlier, and I didn't say a lot about it, but essentially we wanted to do data assimilation. The buoys have sense data. We want the sense data to be on-the-fly processed. That's already the case, but we want this to be fed into a computational fluid dynamics system that will be computed by essentially the cluster at sea, and use that as a way to guide the swarming. And lastly, as well, related to our work with Pablo, we want to go underwater because, you know, the surface is nice, but there is a lot of things going on underwater. Thank you very much.
Okay, let's have the next speaker set up. Professor Whittle.
Roland, this is a great talk. Can you just comment, though, on you talked about scalability in terms of numbers of the sensors, but for me, scalability on the marine phenomena is on the physical scale. It's a very large scale, so I can imagine while you're communicating over relatively short distances, you're running tests over relatively short time periods, power is not really a big issue for you, power and communications. But if you were to extrapolate this to, you showed us a picture of the Barents Sea, with an algal bloom, hundreds of miles of, hundreds of kilometers. What does scalability mean on physical length and time scales for some of these big problems where you want to track big features? What challenges remain in dealing with that?
Yeah, that's a very good point. I indeed show this, algae bloom on like several hundred kilometers, and our system right now is not capable of doing that. Even if you add many buoys, that's just like impossible. The challenges are, the communication, right? There is no system right now that will allow you to deploy a network over such distances, and communication is paramount for that. So without that critical element of distributed communications over long distances, the system will not be able to perform. So I think at this point it's fair to say that what we have shown is limited to, I would say, kilometer square, several kilometers square, but not beyond that. Now, the scalability I mentioned in terms of the control, this one should be applicable to other systems. But that is, assuming that we have the technology in terms of the communication. And on that side, I skipped that slide because we didn't do much. We essentially used an existing technology. We had nobody in the team that had any knowledge in communication, but communicating in the field over long distances, this is a big challenge. And the water is the same problem. Yeah.
Okay, we have a question there, but let's leave that for the panel session.
Okay, again, thank you, Roland. The next talk, in fact, the word algae bloom has been mentioned on and off both yesterday and today, and we're delighted to have Cendric Leung to talk to us on a talk titled "Monitoring Harmful Algae Blooms in Singapore Waters, Toxic Species." Yeah.
All right, thank you. Good morning, everyone. Yeah, actually, in our project, we are using the ASV, as mentioned by the previous speaker. And we would like to show the results that we have collected using the ASV and the optical sensor that we have done. Okay, I'd like to start with a short introduction to harmful algal bloom, in case there's any people who doesn't know. Algal blooms term is defined as an increase in algal cell density to several thousands of cells in the drop of seawaters, and which are induced by favorable environmental conditions, such as high level of nutrients, good sunlight, and the stratified water column. And when the blooms causes negative impact or harmful consequences to marine organisms and to humans, it is termed harmful algal blooms. And as you can see, some has discoloration, some kill fishes, and some impact other organisms like shellfish. Harmful algal blooms are basically divided or categorized into two types. The red type, which means it discolored the seawaters and caused by high density of phytoplankton species. And on the right-hand side, the toxic algal blooms, which cause shellfish or fish contamination with the algal toxin which they produce through the feeding. And red tide normally cause fish kill and shellfish death as well. And the toxic species normally are harmful to humans when we consume with these contaminated shellfish. In Singapore and Malaysia, we have many areas infected or affected by this kind of harmful species causing bloom in many areas. For example, late 2015 to early 2016, there's an extended bloom of a very toxic species in the northern part of Malaysia. And in Singapore, we have several fish kill since 2009. And we also have an extended Dinoflagellates blooms, which lasted for about 3 months. And in Singapore, we mainly experience the red tide blooms as opposed to the toxic blooms which was observed in the eastern side of the peninsula of Malaysia. as we have experienced many type of blooms in our areas, so far we have 3 fish kills and we have a very big extended bloom, but it was confined to a very small area. And based on this, how are we going to monitor our algal blooms in our waters? And are they predictable? And as we know, blooms are very complex and they move around and they form blooms in patches. And to understand this, we need to understand the dynamics of the bloom formation, their behavior. And thinking of this line, we aim at using new tools, new advanced technologies for monitoring and detection of such bloom. And the project started with getting the kayak to work in the field and optimizing and for measurements of various environmental parameters, including the biological biomass. Our goals are to develop a sampling system using optical sensors, autonomous vehicles, advanced technique for monitoring the environmental changes and also the algal blooms, movement patterns and the dynamics, and also to rapid detect, identify plankton species or bloom forming species using some of the techniques available, such as the some of the molecular tools, which we will show later. And first, I'd like to show some of the blooms which we mapped during the early 2016, and this was toxic dinoflagellate blooms which we found in this small little bay near the Silita Island. And we used the autonomous surface vehicles with optical sensors attached to the bottom of the kayak. We managed to map patches of high concentrated cells in the middle of the channel during the ebb tide about 9 a.m. And after a few hours, we came back to do the mapping again during the flood tide, and the bloom was basically gone. They were mainly pushed into the channel with only a few very small patches at the edge, in the middle of the channel. And for vertical profiling or distribution of the algal bloom, we use the optical sensors, and we measured from all the way from the inner channel to all the way to the mouth of the channel. As you can see from the left plot, during the ebb tide, we see concentrated patches which stretch downwards to about almost 2 meters, and at the outer part of the channel, the concentration was not very high, and during the flood tide, it's quite mixed, and the blooms extended down to more than 2 to 3 meters and at average concentrations. From using this kind of methods, we were able to map the horizontal distribution and the vertical distribution of this kind of algal blooms, because sometimes those blooms are not found on the surface due to mixing and due to the movement of the current and also tidal current as well. And this is the 5 days of bloom tracking and monitoring during the same bloom, which we observed early 2016. On the first day, they are all collected at the same time, different day, about 9 a.m. And on the first day, we could only detect very low concentrated patches around in the middle of the channel. And on the second day, we saw higher concentrated patches out here. And on the third day, 1st February, we saw a very concentrated patch in the middle of the channel. And on the last 2 days, the patches were all spread out and distributed within the channels. However, the high concentrated patches did not go out of this channel and spread along the Johor Strait. It was moving in and out of these small channels. And by using the kayak, we were able to map and study the movement of this bloom. And most of the movement are caused by the wind surface current and the tidal current exchange during the day, especially between the ebb tide and the flood tide. And early this year, we managed to map some of the features along this track that we have done using the optical sensor as well. We detected a diatom bloom. These are the good guys. They are not harmful. And we saw some pattern of accumulation. You can see from this left panel, this is a salinity plot, depth against the longitude here. And from this map, we were able to map what they call freshwater plume. We was from the terrestrial input, and the freshwater started with very high mixing, and it stretched all the way out actually to the mouth of the channel. And at the edge of the channel, we saw accumulation of diatom blooms with high subsurface depth, about 1 meter, with a high concentration of about 20 microgram of per liter of chlorophyll, which is indicative index of the biomass of the diatom bloom. So from our transect, we were able to see this kind of features, like, for example, blooms hiding beneath the freshwater plume, and we were able to map the whole stretch of the water plume and see how this the ecosystem in this channel recover back to its original states after 5 days of sampling. And for detection of the bloom species, we used the real-time PCR, and we actually used and tested this system in the field by spiking with the some of the cultures and did the measurement in the field. And this method actually works quite well. It could identify the blooms forming species, and it is a very rapid detection method for target species, and it could be done in the field, and it could use simultaneously to detect several harmful or bloom forming species. And some of the results which we were able to conclude from the monitoring using such instruments that in the tropical areas, these toxic Caronia mikimotoi blooms at higher temperatures, and it also could form blooms with other species such as diatom, but they are the dominant species within the phytoplankton community. And actually they form blooms after heavy rainfall, and they could grow or multiply very fast with the surplus of nutrients such as the nitrogen sources, which were transferred or introduced into the marine ecosystem through rainfall or through flushing and other means. And as compared to other regions such as species from Japan and Korea, similarly, they bloom at higher temperature. They also could form or cause bloom with other species, and they like lower salinity, and they prefer supply of nitrate. And temperate species tend to cause fish kill and shellfish mortality as well. We have not observed any fish kill caused by this species yet in our waters. And we also started the long-term monitoring at a monthly basis from January 2016. This is the total diatoms, which exclude the toxic species. And this is one of the toxic species that we are monitoring, the fish killer. These are the 2 fish killer species, and this is one of the toxic diatom species which we found this year, and at a relatively high concentration. We have never seen such high concentration before, and this toxic diatom actually it is known to produce domic acid, which is very harmful to humans. And we were not able to capture the actual bloom based on the monthly resolutions. However, we did, during this bloom, we have the daily resolution as well. It captured quite well the bloom peaks and the high concentrated patches. But with the monthly resolution, we could not capture the very high cell bloom, very high cell density patches in the Silita areas. This slide shows the number of species that were documented and confirmed in the Western Pacific regions. And Malaysia has the highest number of Pseudonesia species documented and confirmed. And Vietnam, China, Malaysia is about 12 to 17. The rest of the regions only documented species less than 10. In Singapore, we have confirmed 5 species. And out of the 5, 3 of them are able to produce toxins. And these toxins normally known to cause amnesic shellfish poisoning, which is quite harmful to us. And so far, this shellfish poisoning has not been reported in Southeast Asia. And actually, these domoic acid producer are widely distributed in the tropical regions. Some of the trend of these newly found or documented species in our waters is that they are increasing in frequency and durations due to changes in climate patterns, also the nutrients regimes in the marine system, and they cause blooms in many areas around the world. And one example is that they formed the largest bloom along the west coast of the United States in 2015, and many of the beaches and shellfish were banned due to the contamination by the domoic acid. And some of these bloom caused death, and it could cause brain damage and some lung problem as well. And for monitoring, I think it's very important to include these species in our monitoring program in order to mitigate or prevent poisoning cases. And lastly, I'd like to summarize and conclude some of the work that we have done. As we have seen that the frequency of blooms associated with fish kill has increased in our waters. And due to the complexity of the blooms, sometimes we do find multi-species in the bloom, so it is quite difficult to mitigate or to predict them due to the multi-species blooms which we experience in our waters. And also the toxins which causes harm to other organisms, mammals and humans. And are we able to eradicate this kind of algal species? Currently, there's no single method that can be used to stop bloom. However, we could prevent new introduction. What we can do currently is to mitigate or to introduce control, prevention, to reduce some of the nutrient loads into our system. Lastly, I'd like to acknowledge the groups which helped or contributed to this project, especially the SENSEM engineers with their support, field support, and also TMSI staff, students, for their contribution to the project as well. Thank you.
So while Pablo sets up, are there any questions from the audience? Oh, yes, one.
Hi, Sandrick. Thanks for the talk. I noticed you said that you did qPCR in the field, And I was wondering if you might just say a couple more words on that. In particular, I was wondering if you found that it was efficient to do qPCR in the field, because the alternative would be to collect your samples and then take it back to the lab. And if so, what is the setup that you use? What is the piece of equipment? And is this something that you think is going to be part of like a in situ monitoring framework?
Oh, actually, we use the portable qPCR machine, which we borrowed from the one of the distributors. And why we use in the field, because sometimes there's a need to identify the species. If we could, for example, like the Pseudonychia species, right? Some are not toxic, some are toxic. So if we could confirm it is toxic in the field, we could take more samples for measurements in the lab. Yeah, that's one of the objectives that we have. And for using it as in monitoring programs, that's what you meant?
How long does it take to get your answer from sample to answer in the field?
About 2 hours, I think. Yeah. Including extraction, I think. Yeah. Or you can visit our poster if we have, yeah. And Li Ying will explain to you more, I think. Yeah. Thank you.
Any more questions?
Okay, let us thank Cedric again. It gives me great pleasure to introduce another presentation from SUTD in these workshops. I should note that the SUTD has been around less than half the time that CENSEM has, and to see investigators from SUTD presenting is quite a delight. So the next talk is titled New Soft Robot Technologies and Their Potential Environmental Applications by Pablo Valdivia y Alvarado. Please.
Thanks. Hello everyone. My name is Pablo. A little bit more about myself. I used to be a principal research scientist at CENSAM up to late 2015. I used to work with the Michael Trentafilu, Nick Patrikalakis, and George Barbastatis groups. And I joined SUTD. I'm now part of the faculty at the Engineering and Product Development pillar, along with Roland. So today I'm going to talk about some of the work that I've been doing in my group since I left CENSAM. Let me start first with a short caveat. While most of the talks in this workshop have been very close to the field of environment and environmental studies, my work in soft robotics, of course, it'll start closely, I guess, aligned with the environment. But for most of the talk, I will deviate a little bit from the topic, but I'll try to converge again towards the environment towards the end of the talk, and I hope it's entertaining for most of you. Okay, so having said that, let me just start by motivating what I'm going to talk about for the rest of my time. And it's related to the idea of monitoring the environment, right? And I guess this doesn't come to a surprise to most of you after hearing the talks yesterday and today. The environment and pollution are a very complex system, right? There's a mix of chemical, biological, fluid mechanics phenomena, and measurements are key to understand these systems, right? Unfortunately, the hardware that is available to us at the moment to gather these measurements is not ideal, right? We can do better. And primarily the hardware that we have available to us lacks adaptability and robustness. Anybody that has worked in field studies can attest that right now it's inconceivable to leave a sensor unattended in the ocean for more than a week, especially here in Southeast Asia, that the ocean is so rich in life. Biofouling is a big problem, right? When you leave buoys in the coast, if you come back after a week, you're gonna see a little microcosm growing next to your hardware, and you have to maintain, you have to baby the hardware to be able to have it working. So it's inconceivable to leave something on its own for a couple of months, a year, and more than that, right? So that was a big inspiration to develop tools to achieve that. So our objectives were to use advanced robotics tools to enable this long-term exploration and monitoring of the environment, and in more generally speaking, unstructured environments. And if we can do this, there are a couple of interesting ideas that we could explore. And let me give you one example. And I'm going to motivate this with an analogy to fluid mechanics. When you're trying to understand fluid dynamics phenomena, in this case, for example, vorticity, and I'm showing here data, the velocity vector field that we somehow captured in an experiment. If we look at the data, the velocity vector field that is in an Eulerian reference frame, right? This is the reference frame of the lab. We can sort of see that there is some rotation going on, but we cannot really see the boundary of the vortex. We cannot do any further quantitative analysis about the momentum of the vortex. It's where it doesn't help us that much. Now, if we look at the same data from a different reference frame, a Lagrangian reference frame, that means a reference frame moving with the dynamics of the flow, we can more clearly see the dynamics that are there, the vortex, right? We can clearly see the boundary, therefore we can do some calculations about the momentum that this vortex is carrying, and we can essentially understand better what's going on, right? So that's the motivation, ideally. If we can have a way to have measurements that track the interesting dynamics in the environment for long enough, we can reveal some interesting phenomena that might be present there. But to do that, we need to, of course, develop devices that are capable of being there in the environment, measuring things for extended periods of time. So my objectives were to track, of course, and reveal the environment dynamics using robotic markers. And to do that, we need to exploit various aspects of robotics: agility, robustness, awareness. The general idea was to have this fleet of soft robots that were acting more or less like plankton, right? That were basically being carried around by the environment dynamics and performing measurements while deployed, and measuring interesting things such as temperature, salinity, dissolved oxygen, nutrients, etc. And of course, it shouldn't come as a surprise, given the title of my talk, that I am offering the thought that soft robots are a good way of accomplishing this. Well, some of the soft robots, why is that? Because some of the soft robots we're developing provide a very robust base for vehicles that can be deployed for long periods of time. Some of the soft sensors that we can fabricate give us feedback that currently sensors cannot provide, and this is some work that I started back when I was working with Michael. Also, some of the flexibility that is afforded to us with soft robots open up new locomotion capabilities, and especially in unsteady locomotion using large flexible fins as propulsors. So what are soft robots? Perhaps not everyone here is aware of this field, so let me give you a short introductory slide. These are some examples of soft robots. The main difference between soft robotics and traditional robotics are the materials. Whereas traditional robots are assemblies of discrete, stiff components where a lot of metals, composites, hard plastics are used, soft robots primarily use polymers, hydrogels, very soft, squishy materials. These are some examples of my work at MIT. This is a walker developed by the Whitesides group at Harvard. This is the Octobot at Harvard too. This is a tentacle manipulator by Daniela Ross's group at CSAIL. This is a soft gripper by iRobot, soft sensor by Carnegie Mellon, an example of a hand, robotic hand. You can think of soft robots as composite structures, right? So the materials that you use play a key role on the performance of the robot, whether it is locomotion, grasping, manipulation, sensing, etc. Another interesting feature, so I have a movie here. I have a movie here that I want to show you guys, but I'm not sure if it's going to be able to play. laptop doesn't crash on me. Anyways, let's see if it plays now. If not, I'll just skip it. Well, another interesting byproduct of soft robots is the materials we use, polymers, hydrogens, and polymers we primarily are using now, silicons, are relatively impervious to biofouling. We've done some studies with DSO, for example, where we place some samples of these materials for long periods of time, for a month almost, in marine environments here in Singapore, and you can see very little biofouling has accumulated. We put, I don't have the pictures now, but next to these samples we put regular metallic components, and of course after a week these are unrecognizable. Okay, so this is where the talk starts deviating a little bit from the environment. So I mentioned that we're proposing soft robots as an interesting new tool in advanced robotics to do useful environmental studies. The performance of soft robots is very closely related to the materials we use, basically how we fabricate them, right? So how do we fabricate currently soft robots? So I'm calling this making robust hardware 1.0. Currently, the fabrication of soft robots relies primarily on casting, right? We find the distributions of these polymers that we need in the body to achieve locomotion, sensing, etc. And we make molds and we cast the components required. This usually happens in various types of setups. We cast different components in different machines. Then we aggregate, we assemble the robots. So the resolutions tend to be low. Multiple steps are involved. The geometries that we can achieve are fairly limited. It basically depends on how good we are at producing molds. The materials that we currently use, again, these polymers, hydrogels, in general have limited or no functionality. They primarily provide structural properties. Additive manufacturing, AM, provides multi-material printing possibilities. Maybe you are familiar with the PolyJet printers from Stratasys that can print various materials ranging from things that feel like thermoplastics to some materials that feel more rubber-like. Unfortunately, these materials are UV-based polymers, which means that these materials remain sensitive to UV for the rest of their life, so you cannot really deploy them in the field, especially here that we have so much UV in the environment. They will degrade. They provide very low strains. They break at around 50% strain. Most soft robots see strains upwards of 100%. So there's some challenges. So what my group has been doing is trying to develop new fabrication approaches to enable adaptive and functional features to soft robot bodies, and we're calling this making robots hardware 2.0. And we're doing this, or we're trying to do this by essentially developing tools that allow us to do direct fabrication of multi-material soft composites, right? With steps that will allow us to carefully tailor the material properties, and I'm talking about broadly speaking material properties: viscoelasticity, density, chemistry, biology, electrical properties, magnetic properties, etc. All these using materials that are still capable of large deformations and are also resilient to the environment and to UV. And the functionality that we want to endow these soft composites involves basically adaptability. We want to have devices that can show large, fast, and reversible material property changes, and as well as morphological changes. And I'm giving you some examples here of the types of robots that we're currently building, right? They have embedded sensors, embedded actuators. They can morph. So some of the ideas we're exploring are inspired by a cartoon, an old cartoon that I used to watch when I was a kid. This is actually older. This is from the 60s. It's called Milton the Monster. We got it back in the 80s in South America, where I'm from. And it's essentially, it presents a very interesting fabrication approach, right? This is a mad scientist that makes monsters, but you can think of them as robots, right? Automata. And you can see that essentially using a lot of chemistry, right? He has a mold, he puts some chemicals, and boom, voila, you have an automata, in this case Milton. He made the mistake of putting too much a potion for the heart, so he's a rather caring monster. So it's a fun cartoon. 50 years after this cartoon, we actually have the technology to do this. And it's coming, for the most part, from bioprinting. We have various tools that allow us to direct deposit and direct print various materials. For the most part, these technologies have been focusing on materials that can support living cells. This is to test tissue scaffolds, to test drugs, etc. Unfortunately, most of the materials that are used in these approaches are not compatible with oil-based materials, with silicon. That's the bedrock of soft robotics. So my group is working on trying to adapt some of these tools to be used with silicon. And our concept is, in a nutshell, presented in this slide, right? So when we want to build a particular robot, we use FDM, which is a type of 3D printing, to print a mold. In this case, let's call this little container the mold. We print it, we fabricate it in place. In the same machine, we deposit a matrix material that's going to be the foundation of the body. We fill this mold with a material. And then using various dispensers, we proceed to embed different features inside this body using different patterns, right? And these inks that we use to embed patterns can have various types of material properties, right? And they can be isotropic, anisotropic, and can have other interesting properties as well. And the idea is to end up with anisotropic material distributions and bodies that are essentially soft composites, right? And these are some of the examples of the types of composites that we can fabricate. We can also combine multiple matrix materials once a given layer has cured. So this is, in general, the concept. Let me give you an example, actually, of how we apply this to build one of the stingrays, the little stingrays. So this is the setup where we 3D print first the mold for the stingray using FDM. We place some internal components. We then deposit the matrix material for the body, and then we embed some features. In this case, we embed features inside the fin to allow us to tailor the kinematics of the fin so that we can improve swimming performance. So this is the machine. These are as an example of one of the machines we're using. We're essentially hacking commercial 3D printers. We're adding a bunch of dispensers. We have XYZ positioning with a heated plate. We have hot filament extruders to 3D print using various thermoplastics. We also have cold extruders to 3D print clays and plasticines. And we also have a variety of high precision pressure control dispensers that allow us to print with these various inks, right? We can also do subtractive manufacturing with a mill head and a laser. So the bottom line, these are cheap. These are affordable. You don't need to spend $500,000 in a machine to fabricate this. I had to show you this quickly. You might think, well, what's the big deal? Cake makers have been doing this for years, right? Like happy birthday on top of your cake. Well, actually, the fluid mechanics is a little bit more complex than that, right? We're embedding a highly viscous ink inside a highly viscous body. Why viscosity? Because once we write or we embed something inside, we want that feature to remain in place, right? So viscosity plays a big role. Of course, as we print, we don't want any crevices created by the dispenser, by the needle of the dispenser. We don't want any crevices to remain there, right? So we have to take various considerations on the fluid mechanics and also functionalize both the materials for the matrix and the inks. In a nutshell, I'm going to try to summarize this. We're using non-Newtonian. We need to make both the matrix and the inks non-Newtonian, shear thinning, so that while no stress is applied to them, they remain in place because of the viscosity. But when we apply some shear stress on them, for example, when we are depositing them, the viscosity is low enough that we can extrude them easily, right? So these are some examples of the types of features that we can embed 3D print. And at the moment, we're not too concerned with the resolution. The smallest thickness of features that we can print are in the order of 100 microns. The spacing between the features are also of the same ballpark. We can make very sharp turns, so we can print 90 degrees without a problem. These are some examples of the arrays. We can functionalize to the inks to display luminosity. And I'm writing SUTD in one of those samples. So we have gotten very good at doing this. We can also print self-intersecting paths. We, of course, want to characterize the various performance we can achieve with these composites, right? Whether it's mechanical, chemical, biological. This is an example of the mechanical tests we are developing based on this ASTM standard to characterize the composites that we can create. And we developed simple models, again, to also try to estimate, in this case, the material properties of the composites that we print and compare them with experiments. I'm going to skip through this because I think I don't have that much time left. In terms of design, there's many interesting things that we can do as well. Once we have a target kinematics in the case of locomotion that we need to achieve, right? Or for sensing, it can be a type of sensitivity, or for actuation, it might be a stress generation, etc. We essentially do an inverse problem, and we try to we solve for the material distribution that is needed to give us that performance. Right? Now we have the problem of what is the best way to achieve this material distribution, given that we can print almost anything inside the body, right? How do we optimize the geometries that we use? How do we optimize the density of the material that we use? The material combinations, printing speed, materials usage, etc. All these we're exploring. And let me give you, I'm going to finish giving you a couple of examples. This is how we use this approach to functionalize the bodies of the stingrays. We essentially print these composite features on the fin to tailor the fin kinematics. And we do this because this allows us to control the thrust generation. And the movies here show various stingrays with and without the features embedded. And if we plot the amplitude envelope of the kinematics, we can see that the composites actually make a difference in tailoring the kinematics, and the resulting thrusts are noticeable. The resulting changes in thrust are noticeable, I should say. So that's for agility for locomotion. We use this also to make sensors. The whiskers that we continue to work in collaboration with Michael's group, we're making soft follicles. In this case, the ink now is a combination of platinum catalyzed silicon with silver. So it's a conductive ink. So by changing the geometry, we can essentially have features that are resistive. The resistance change given the stress applied to it. So we can measure normal tangential stresses, and we use this on the follicles of the whiskers that we're developing to put in our soft robots. And this movie just shows how the resistance change when we're applying a stress. Finally, more in line with the environment, nutrients are a big deal. Sandri just mentioned, right? The abundance of nutrients is one of the indicators of the onset of algal blooms. One of the inks we're developing also uses ionogel-based gels to detect nitrates. And we're using this Grace reaction, right? And in a nutshell, the way it works is the gels are doped with two ions that react with nitrate in the environment, and that when the reaction takes place, there's a production of an ink that allows us to visually identify the presence of nitrate. So let me finish just by listing, of course, we're still, this work is ongoing. We're working on various areas on manufacturing. In terms of deploying this in the real world, of course, we're doing more work on control. Roland mentioned that we're going to start a collaboration soon where we're combining swarming with some of our hardware. Power is an issue too. We're working on printing batteries, soft batteries inside the bodies of the robots. Computation as well, soft computation. And we're still, I should mention, we're still developing inks. We're actually developing an ink that is a type of hyperelastic bone. It has the same flexural rigidity and porosity of bone. So let me acknowledge my funding and thank my team. And that's all for me. Thank you.
So maybe we have time for one question while the next speaker is setting up. I have a question actually. So you mentioned that the soft robots could go up to order of 10 meters in scale. What are actually the largest soft robots there, and are there issues in terms of scaling the amount of skeleton versus as you increase in size?
No, I didn't talk about the scale. So when you talk about the scales, there's various considerations. One is, can you fabricate that large of a soft robot? And also, what is the, say you're talking about locomotion, right? Is the locomotion that you're trying to fabricate going to be useful at that scale, right? So the robots that I showed they swim using large fin deformations, right? So they essentially the type of locomotion that works well at high Reynolds numbers. Right? The largest one that we have built of that type of robot is a Stingray, and it has a diameter in the order of 1 meter. The smallest one we built is a couple of inches.
Thanks.
Thank you.
So before we thank Pablo again, I have a quick comment. To be serious about what you intend to do, you should call the hardware of your soft robots software. Because you keep saying hardware, soft robots, they're software. Okay, this is half in jest. So I'm delighted to welcome Serena Teal, who's going to present the last talk of this session. She's with TSMI of NUS and also director of St. John's Island's National Marine Laboratory. And her talk this morning is Challenges for Marine Science in the World's Busiest Port. Yeah, we welcome you.
Thank you, Dick. Okay, can you hear me? All right. Well, I'm not going to hold you back from lunch, so this is a very light presentation. Thanks to Janelle for inviting me. She gave me an awful challenge. She said, oh, can you present all the projects in TMSI over the last 10 years, and after that, talk a bit about the future? I'm going to fail miserably at that. Okay, so what I'm going to do really is just to give you an overview of some of the work that has been going on in TMSI, funded by CENSAM. And after that, talk a bit more about the marine science program that is unfolding over the next 5 years. In terms of projects, so I think on behalf of all the researchers at TMSI, we would like to also thank all our collaborators in the CENSAM project. Okay, moving forward, I guess some of you who maybe you have recently come to Singapore, and I think maybe after a few months you might realize that actually this is a very strange country. There's something unusual about it. And I would say the first thing that maybe I should tell you is that actually this is the third densest country in the world, right? The first is Macau and the second is Monaco. And you appreciate that those is quite a different scale. In Singapore, we are a very small country. There is only about 700 square kilometers, in which right now there are 5.6 million people, excluding the tourists, right? So that's a lot of people. That's about 7,000 over persons per square kilometer, which means that for every 100 meters, you should see at least 1 or 2 persons. What perhaps many of you don't realize is that actually the sea is even worse. At this moment in time, we actually have more land than sea due to reclamation. Singapore itself has actually grown by 25% of its original size. So there's about 600 square kilometers of sea, except that there are 1,000 vessels in that 600 square kilometers, which means there's really 1 vessel in every square kilometer. So like many of you who are actually trying to develop applications for the marine environment, I think if you've actually gone out to do field work, you would find that it's quite hazardous. There are these big speeding vessels, right? You very seriously have to care about them. So what it works out to really is that there is 1 vessel coming into the port of Singapore every 2 minutes. So it's a very high traffic situation. We're talking about a marine environment which is equivalent to standing in the middle of the highway. And I think that this context is very important when we do marine science. I think In Singapore, I always say this is probably the few countries in the world where one actually has a discussion about where you should go swimming. I personally wouldn't, right, because of the industries and chemicals. But it brings to you this huge challenge, high density population, and a very narrow strip of water. Think about all the anthropogenic contributions into the coastal waters around Singapore, as well as overlaying that the huge numbers of people and activity going on in a small water body. Bearing in mind that Singapore's coastal waters is very small, so geographic separation of activities is not feasible. It is the same water body going back up and down that area. Now looking maybe a bit further afield, it's also good to put things in the context of Southeast Asia. I like this map. This map comes from the Globalis program. All the little yellow dots are ships in a point in time, right? That's the shipping traffic in the South China Sea. All the big red dots are megaports coming up around Southeast Asia. And the little white dots are what we call marine protected areas. And I think one of the first things you appreciate is that really isn't any separation between the three. This is also, the South China Sea itself is also what we call the mega biodiversity hotspot in the Amazon of the marine world. So all this is overlaying each other. So when we study marine science, we have to be very aware of these issues and how they interact. I also like to bring up this map. This is a map drawn up looking at global shipping. And one of the things that ships are these huge things containing about 12 swimming pools worth of seawater, and they carry this water from one port to another. So one of the major things as for Singapore as the world's global top transshipment hub is that we are also an airport for organisms coming in and out. And in this year, in fact, it's been pointed out that Singapore is one of the major high-risk ports for transfer of invasive species between countries. At the same time, on the terrestrial side, due to urbanization, it already we are within the top 5 countries with invasive species present on the land side. In the marine environment, so far, the impacts have not been there, but it is a real risk. Okay, so in terms of projects, I'd like to sort of take a snapshot of at least of the past 5 years, the projects that have been funded under SENZAM. It's very broad. You see, we've had projects on environment sensing, modeling of the South China Sea, and more recently, food security has come up very much. And I think maybe this is also a very just today and yesterday, I've actually spent the whole of yesterday at the Urban Sustainability Conference, and that's where I thought that when I came to think about doing this lecture, it also made me think a lot about when we talk about marine science and urbanization, that over the last 5-10 years, certainly through the SENZAM programs, we have learned a lot about the marine environment. And going forwards, we also start to thinking about the urbanization and the impact of marine environment and urbanization. So I'm not going to describe all these projects in detail. Many of the colleagues who are participating in these projects are actually here in the audience, and I'm going to leave you to attack them for questions. Just tell me which project you want, and I'll point out the researcher. A quick snapshot. Definitely, in the earlier phases, there was a lot of work on hydrodynamic modeling, and I would say that through the SENZAM projects, we actually have now a very good snapshot of the environmental processes in the South China Sea. This is very important in the context of Singapore because the seasons in the sea here are all monsoon-driven. And so through the SENZAM project, we have actually now a very good map of the environmental parameters that affect Singapore. Singapore is actually biologically in a very interesting point. we kind of lie between two oceans. And in biology, we always talk about this as being in a fulcrum between the Pacific Ocean and the Indian Ocean. And actually, when I look at biology, we have always noticed that we've had a bit of both. Many of these hydrodynamic models now actually help very much to explain why you see this change in fauna in Singapore. It's just from the way that the currents pass across Singapore. And in terms of biology, again, I think my colleague Cendric has already mentioned a bit, and these high-resolution models are also very important in our understanding of simple things like how algal blooms form. In the case of dinoflagellate blooms, for example, I have learned that estuary fronts are actually a very big reason way. Well, they're very important to how dinoflagellates get together in sufficient numbers to actually cause an impact. They're a bit different maybe from diatoms, which are more dispersed. Cendric already has gone through this slide for me, so I don't really need to go through it. Other projects include my colleagues in ARL, doing very nice work. What they've been doing is making use of snapping shrimps. Just a footnote, those of you who think that the sea is a very nice, quiet place, I also like you to know, I've also discovered from my colleagues in ARL that actually our marine environment is a very, 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 very noisy one because of the industry. But at the same time, there's also this huge background noise of snapping shrimps. Apparently, they are very abundant around coastal areas, so much so that they can also be used to start mapping structures in the sea. So this work is actually quite interesting, that they can actually use snapping shrimps to image the coastal areas. More recently, there is several of my colleagues are involved in food security projects, starting with looking at flooding in different seasons in different cities, now moving on to looking at rainfall in much larger scales in the South China, in the countries around the region, in relation to food security. And food security, by the way, has actually been identified as one of the key areas. I think yesterday the minister talked about cities of tomorrow, and one of the big anchors in that program is actually going to be the food security program. Okay, so now going forward, I would just like to, maybe for those of you who haven't already heard about the Marine Science Program, to tell you a bit more about the programs. It pretty much unfolded somewhere around 2015 when we started talking about marine science and the relevance of marine science to Singapore. The NRF since then sort of looked into it. Why is marine science important to Singapore? Most of the research in Singapore has always focused on mainland Singapore, on the idea that we have very little coastal water. But Singapore is an island state. Interestingly, we are in an area, as I mentioned, at the edge of the Coral Triangle, in which there's a very high biodiversity. And as a huge transshipment hub, you can imagine we are also transferring a lot of this biodiversity to everyone else and distributing it in not so nice ways. Climate change is a big issue. Climate change will affect the South China Sea, and most countries in the South China Sea depend hugely on the ocean resources. So it is an issue that Singapore cannot ignore. The next aspect that was brought up was that most of our neighbors do have what we call bread-butter issues, and maybe in that sense, Singapore has a bit more luxury of thinking about marine science and looking at higher-end R&D research. So it has sort of a first-mover advantage. And for example, NRF brought up that there are already existing partners in Singapore with a fair bit of infrastructure through the Senzam program, through TMSI, through SELSI. So the R&D infrastructure is already pretty well set up for marine science. The key themes that were identified, well, after a lot of long discussions and arguments over what programs should be included and not included, I would say first First off is that anything that's already funded by an existing NRF program cannot be part of the MSRGP. So we were a bit constrained, but these were the three main pillars that were identified as important. Basically, firstly, marine biodiversity. From the NRF perspective, they are sort of looking beyond monitoring, right? What's the fate of our biodiversity going forwards, climate change, for example. And I think the other maybe interesting thing for those of you technologists in the audience, one of the big questions the chief executive said to me is, so what can we do with all this biodiversity? Right, so those of you interested in biomimetics, he's looking for proposals, right? He's serious. There's all this biodiversity. Can you do something with it? The second pillar was an environmental impact assessment. We agreed that, yes, there are many monitoring programs going on, but I think the overall sense was, can we do better? We need to improve the quality of the information that we are collecting. EIA is a very big business in Singapore. Many companies come to Singapore and from here work in the regional countries. So for example, DHI, Deltares. So in that sense, R&D, any R&D to improve the way environmental impact assessments are done is very welcome. The last one, coastal engineering. Coastal protection is also a another big pillar inside the Cities of Tomorrow research program that was launched yesterday. So, with climate change, storm surges, there are going to be all these big ugly walls. Can we do better? Can we integrate greenery? Can we restructure shores? So these are the three main pillars for the program, for the current 2016 to 2021 program. So where St. John's Island Marine Lab came in was simply that, well, actually in terms of infrastructure, research infrastructure, the institutes in Singapore already have a lot of equipment, a lot of expertise, a lot of technologies. And so where the Marine Lab really fits in was to provide seawater facilities for people to conduct research. Just earlier, Stefan was talking about NUS and NTU having to work together. Well, I have an even bigger challenge. The NRF would like everyone to work together, right? Including SIT, SUTD, and all the polytechnics. Because one of the big issues that came up when we started talking about marine science was that if we sat down and counted all our marine scientists, we don't actually have a lot of them in Singapore. So there was, in that sense, a great need, in order to push marine science forward in Singapore, a need for every person who is doing any marine thing to get together. Many of the problems are hugely interdisciplinary. So in that sense, one of the roles in the Marine Lab is also to try and all of you who are interested in marine-related stuff to let us know so that we put people in contact whenever there are grant calls or any interests. We know who to send out the information to. So the Marine Lab, I welcome all of you to visit, right? Just contact me or one of my staff. We have already set up the website. Very simple process. You don't have to collaborate with NUS to use it. You just need to go in, register, and you can start using the facilities. Why are we in St. John's Island? Why can't we be more conveniently located? It's very simple. That's about the only place we can find with fairly decent seawater, right? It's facing the strong currents in the Singapore Straits, so at least there's a reasonable, good quality water. The other big thing that maybe some of you may not appreciate is actually the Sisters Island Marine Park. As I mentioned, Singapore has been reclaiming land and a lot of reclamation, a lot of urban development. And one of the major consequences of that is that it has prevented a lot of long-term monitoring. If you speak to my colleagues, they will tell you that when you start out your project in a location A, it may not exist by the time your project finished. Some works or something would have come and changed it. So doing long-term monitoring has always been a challenge. The Marine Park was set up in 2014, and that actually now presents a huge opportunity for people who are interested in longer-term monitoring to set up systems there. At least it gives us all a stable point in the marine environment of Singapore to use for research. Right now, I think this is a short list of the projects in the first round of the Marine Science R&D program. It's quite broad, a lot of emphasis on climate change. The second round will be results will be released in July, right? So if you go to the MSRDP website, you will be able to, you'll find out what the next tranche of projects are. For those who may not have been shortlisted, the good news is they are also launching a huge slew of internship programs. So inspire your students to take up a project that benefits you, right? They are going to be given student grants to do projects here as well as going overseas. Also, for those of you who are graduating, I think they've only barely finished recruitment for round 1. So with the launch of the news, I think there are 12 projects in the second round. There are definitely a lot of positions for RFs and research assistants. So definitely keep an eye out if you're looking for a job. And with that, I would like to end maybe with something that Professor Chow Luk Meng always said. In Singapore, we always think that there's nothing left to do. I mean, there can't be any biodiversity left in the sea to care about. Like Prof. Chow said, the corals are still spawning every year, and they adapt. So it's ours to try and do what we can to protect and conserve the marine environment. Thank you.
Are there any questions for this particular talk? No, or let's invite all the speakers to the stage. There was a question there earlier that we didn't have time to get to.
My question is to Roland. I'm curious about the material of your autonomous buoy.
You're referring to the hull?
The exo material.
It's made of aluminum.
Aluminum. So was there, how did you manage the biofouling on the material? I mean, that something you can share with?
So what I'd like to say about this, the choice of material was how can we get many of them manufactured at low cost. We looked into plastic, and it was complicated, very expensive. So we went for, it's not like we specifically chose aluminum. So it was just a default choice by a contractor in China that was able to make it in large quantities. It's pretty heavy because it's quite thick. It's probably not the best choice. We're looking into other options right now. So in terms of biofouling, now to answer your question specifically, we went to St. John's Island only once. And not for a long time, unfortunately. I won't be able to comment on that.
It was something that you didn't face?
No, that's something we should consider, definitely. Yeah.
But Dr. Pablo, is there any, apart from the material themselves, was there any coating stuff that you managed to do on?
No, just silicones are by their nature resilient to biofouling. Okay. And actually, Roland and I are going to collaborate in this long-term study, so.
All right, okay.
It just so happens I work on biofouling, and so silicon is actually a pretty decent material. So like most of the shipping now is using this, what we call non-stick surfaces. Most of them are silicone coatings, right? So it's just a case of maintaining and not leaving it in the water static for too long.
And actually related, so I mean, I came across something. So basically, when we install underwater cameras, around underwater cameras, when there is certain movement in the water itself, there was no biofouling that was found. I mean, is there some study related to marine life behavior that somehow biofouling doesn't happen or something towards that? I'm not sure if I'm
not aware of it, but it makes sense, right? Biofouling is essentially you have a fauna, right, that is growing in a surface. So if the surface moves, right, so it's going to disturb the growth of anything on it. So it cannot. It helps, right? It doesn't hurt if the surface is moving.
all right. Okay, thanks.
Other questions?
First of all, I'm a co-PI from NTU with Eric, and I would like to thank the support of CENSEM. Has been a really pleasure to work in the center. And I think it's also that we are seeing our students being employed, finding jobs and so on, so it's great. Actually, my question is to Dr. Pablo. I've been also playing around with this soft material in the lab, using BDMS and changing density by using oil, mixing with oil, glycerin, and so on, and monitoring their property over time using rheometer. And typically, I think that they change over time. So, so with your intention of using this soft robot for a long term, for a long period of time, how do you guarantee that their property will not change?
Yeah, that's a good question. At the moment, we don't have a good answer for that. It's true that over time, the materials would soften up a little bit. Especially if they're immersed in water, if you leave them outside, they'll harden up a little bit. So long as the variations are within a certain range, we think we can cope with some of those with control, right? Of course, the variations in material properties are going to affect some of the kinematics, the motions that we can achieve. So if the variations are within a certain healthy range, we believe we could still contain those using control. If they're larger than that, yes, it's a serious problem, and we're going to have to look into extra chemistry that we can develop for the materials.
Thanks. Hi, so first of all, Sarita, I just wanted to say I really enjoyed your talk, and that sets a fantastic context, I think, for the marine research that we had heard about earlier. And within that context, you had showed this picture of just how busy Singapore is in the marine space. And I was wondering, within that context, Pablo and Roland, what does that actually mean for you guys? Because you do your work in reservoirs, to show these distributed swarms working and more controlled systems. Is this going to be a problem for implementing these kind of heterogeneous swarms out in the busy coastal environment? And will they need to have sensors for seeing if ships are coming, or what does that mean for you guys?
I think that's why this new lab is very attractive to us, because it's somewhat of a sheltered, real marine environment, and we are trying to get funding from NRF in this regard. So,
well, I got permission for you to use the lagoon.
Actually, from my perspective, we just want to add to the business of the port, right? So, like many swarming agents, that would be just busier. So, just without kidding, the systems we're looking at are very small. So this is not a massive cargo, hitting into a battleship. It's so small that if you have a ship passing by, it will be moved away. So the chances for collision, I think, are limited in a sense. Now, when we had some initial contacts with MPA, the Maritime Port Authority of Singapore, And they are very concerned. You know, having objects like this, they look like a mine, right? So they're just worried, like, I mean, think about all these people coming from all over the world, and then they come to the waters of Singapore, and they see all of these, you know, buoys. They wouldn't know that it's something just for like you know, research purposes. Trying to make a collision avoidance system that is, you know, really active in responding to the I think it's a challenge. How to comment on this right now? But I think just a passive repulsion is going to happen, just pure hydrodynamics in a sense. Yeah.
I think that it also presents, I call it a technological challenge for, you know, to work within. One of the key, I think, like MPA has been talking about, now we talk about smart nation using sensors, robotics to take over many of these dangerous tasks, like monitoring the port and things like that. Having said that, so in that context, so far MPA has mostly been looking at aerial sensors, because underwater robotics hasn't reached there yet. But that is one domain where, for example, divers, there have been so many dive accidents, but divers have to go into the water to do a lot of these things. And so there is actually within the Maritime Port Authority a huge interest to fund marine robotics and sensors.
Yeah, that's absolutely right. Somehow the MPA recognizes the need to have many platforms doing something. And their perspective is they're so worried about collision that they just want to be above the ships. Now, the air in Singapore is pretty busy as well. So when you look at the map of where you can fly a drone, it's almost like the entire Singapore is a no-fly zone. So it's really busy in 3 dimensions, underwater, you know, the surface of water and in the air. I think we have to make an effort in providing the assurance that the system is not going to be a danger, and they might, you know, be interested. There are many things. They are limited right now in terms of getting information about what's going on, because the using cameras from the shore is just impossible. Like the view is blocked. They want to measure pollution in the waters, for instance, to catch some of the polluters, and they are not able to do it. The flying drones are too limited. The payload they can carry is too limited. You need to recharge them all the time. So it's an attractive solution, but it's probably not as effective as it seems. Yeah.
And I think where they are using, even if one of those things got crashed by a ship, it's not as bad as a person.
Or 7.
Yeah, just on the subject of collision avoidance, I spent a little time in Hanoi recently, and everybody and their cousin has a motor scooter, and they have huge traffic densities, and they seem to be able to merge very well. They seem to be able to get through intersections that are uncontrolled. You've referred to looking at birds flocking. Have you looked at human beings flocking?
So I know we could continue for quite a while because we have such excellent speakers, but I think the thermal comfort of the food is deteriorating as we speak. So with that, maybe we should break and we can continue informally over lunch. And let's thank again.
Let's crowd at the.
Let's thank again all the speakers, and please do intelligent swarming as you go to the food line. Yeah, thank you.